Well, pre-calculus classes, once again, good afternoon, good evening, or good morning, depending on whenever it happens to apply that you might be watching this. Today we're going to start into section 5.3. Much like section 5.2, we're going to be using some trigonometric formulas for this section. And much like the sum and difference formulas from section 5.2, you will no longer be expected to memorize these. But in 5.3, we're going to go over what are known as the double angle formulas. So for these, the first one, sine of 2 theta, is 2 sine theta cosine theta. Now, cosine theta actually has three forms. Now, the base form is cosine squared minus sine squared, which if you look at this, probably looks real similar to something you've been working with quite a bit, and that is the Pythagorean identity. I know with just completing identities, it's cosine squared plus sine squared. So when we work with cosine of 2 theta, you can actually use one of three forms, and those other forms come from the fact that cosine squared is 1 minus sine squared, and sine squared is 1 minus cosine squared. And basically all we're going to do is take each of these and plug into either cosine squared or sine squared. So probably the easiest one to start with, if we plug in 1 minus sine squared in place of cosine squared, that gives us 1. And then when you combine like terms, there are minus 2 sine squared thetas. When we plug 1 minus cosine squared into the minus sine squared, what ends up happening there, the negative distributes, and you end up with 2 cosine squared thetas. And then when again you distribute your negative, minus 1. But again, the top one is what we view as the base formula for cosine 2 theta. You can use either of these as you work through things if one or the other actually is more useful, and we'll even talk about that here in example 2 in the notes. And then the final one, tangent 2 theta, is 2 tangent theta over 1 minus tangent squared. All right. So now looking at a few examples. Well, for this first example here, it says find all solutions of 2 cosine x plus sine of 2x. Well, again, this is going to work a lot like some of the identities you were working with in section 5.1 in that we are going to have to do a substitution. When you have a trig function like cosine x and a trig function like sine of 2x, whatever is inside the trig function, here I have x, here I have 2x. Right now we are not really working with like terms, so what we have to do is change sine of 2x into 2 sine x cosine x. So when we do that, that's going to keep the 2 cosine x as is, plus 2 sine x cosine x equals 0. Now from here, we are going to be able to factor this. There is a greatest common factor. Both terms have 2 and cosine x in common. If I factor 2 cosine x out of itself, that leaves a 1. If we factor 2 cosine x out of 2 sine x cosine x, that leaves 1 plus sine x. Now, when we factor, we can set each factor equal to 0 and solve. So for this one, divide the 2 over. You end up with cosine x equals 0. For this one, sine of x equals negative 1. Now from here, we're basically just going to go back to our unit circle. I know you didn't use that a whole lot with your identities. Did use it some, I'm sure, as you work through 5.2. So we're looking at, okay, on the unit circle, where is cosine equal to 0? Well, once again, cosine represents our x values. There are 2 spots. One of them is at pi over 2. The other one is down at 3 pi over 2. Now, the next thing that's going to show up when we're looking for where does sine equal -1. On the unit circle, again, we're looking at where do our y values, or where does our y value equal -1. It is also at 3 pi over 2. Do not be surprised as you work through these if you ever see some overlaps. Now, you will often see these questions worded in one of two ways. If they want to know solutions between 0 and 2 pi, they are pi over 2 and 3 pi over 2. If the question actually asks you for all solutions, keep in mind, when we're working with the unit circle, well, I have a solution at pi over 2. I can go around the unit circle an infinite number of times. So, if it does ask for all solutions when you're working with some of these on Pearson, do not be surprised if it will actually say something like pi over 2 plus 2n pi and 3 pi over 2 plus 2n pi. And again, all that's accounting for is that I can go around the unit circle an infinite number of times. And when you would need these is if it is asking for all solutions. If it just wants from 0 to 2 pi, then you actually have just those two solutions. So it'll usually be very implicit in the directions as to which one it wants. All right, example 2. I know that in example 2, you saw something similar to this in 5.2. I know there was one where we used u and v, and they were fractions where we had to set up right triangles on the unit circle. Well, this one's going to be very similar to that. So, cosine of theta equals 5/13, and theta has to be between 3 pi over 2 and 2 pi. Well, what this last detail is telling us that if theta is between 3 pi over 2 and 2 pi, when we set up our right triangle, we are going to establish it in quadrant 4. So cosine is adjacent over hypotenuse. Our adjacent side is 5. Hypotenuse is 13. Again, I'm not going to work through Pythagorean theorem. This opposite side will equal 12 when you do your Pythagorean theorem. Now again, the key piece of information, we are in quadrant 4. Sine is negative in quadrant 4. Now from here, it says to find cosine of 2 theta, sine of 2 theta, tangent of 2 theta. The order that you find those in is kind of up to you. I'm actually going to start with sine 2 theta, which is 2 sine theta cosine theta. Well, the sine of theta, opposite over hypotenuse, is negative 12/13. The cosine of theta was given to us 5/13. And then from there, all you have to do is multiply through. The one thing that you do need to be careful about is keep in mind that is 2 over 1. Now just multiply across the top. Well, negative 12 times 5 is negative 60. Times 2 is negative 120. Across the bottom, 1 times 13 is 169. So that is the sine of 2 theta. Now from here, cosine of 2 theta. You can actually pick which of the 3 formulas you choose to use. Because we have all 3 of them, it's kind of up to you. I'm probably going to go ahead and just use the base theorem or identity here, the cosine squared minus sine squared. But you could use any of those 3 that you wanted. All right, so cosine of theta. Well, cosine of theta, 5/13, and we are going to square that minus. Sine of theta is negative 12/13, and we're going to square that. From here, 5 over 13 squared is 25 over 169 minus negative 12 squared over 13 squared is 144 over 169. From here, just combine your like terms in your numerator. 25 minus 144 is negative 119 over 169. So, you have sine 2 theta, you have cosine of 2 theta. Now, here is where you can make the third portion of this very easy or a lot of work. If they want tangent of 2 theta, and you already have both sine and cosine, don't use the formula. Use the fact that tangent 2 theta is simply sine over cosine. So all we have to do is take the two answers we've already found, and this is also the reason why I went ahead and found sine first. Well, for this, when you have a fraction over a fraction with the same denominators, we can cancel those, and we're left with negative 120 over negative 119. Negative over a negative leaves us with a positive. So that is 120 over 119. Again, I do not actually use the formula for tangent if I already have both sine and cosine. If you were asked for this as a freestanding question, that would be the only time I use that. All right. Express sine of 3x in terms of sine of x. Now here is where we are going to combine our new material along with some of our sum and difference formulas. So if you want to take a moment, hit pause, find this page, you might find that helpful. So what we are going to do for this, the sine of 3x, we can rewrite this as sine 2x plus x. And here is our alpha and beta. And now we can use the sum formula. So this becomes sine 2x cosine x plus cosine 2x sine x. All right, so sine of 2x cosine x plus cosine of 2x sine of x. Now we are going to use, since this says sine of 2x, we are going to use our double angle identity. 2 sine x cosine x. And this becomes 2 sine x cosine squared x. Now, when we come over to cosine of 2x, here is where I was saying, if there is one version of cosine of 2x that works better for you, that's where you want to use that. Well, we are asked to rewrite this in terms of sine of x. Our best option now is to use the 1 minus 2 sine squared. So when I substitute there, I am going to make this 1 minus 2 sine squared x times sine x. And now I can distribute. 1 times sine x is sine x minus 2 sine squared times sine is 2 sine cubed x. All right, our final option or final substitution that we are going to have to make is, again, we're going to use Pythagorean identity because we have sine x here, we have sine x cubed here. So the good news is all but this is in terms of what we need. Well, again, cosine squared is 1 minus sine squared. So 2 sine x cosine squared is 1 minus sine squared x plus sine x minus 2 sine cubed x. And to finish, we are going to distribute 2 sine x times 1, 2 sine x, minus 2 sine cubed x when I distribute there, plus sine x minus 2 sine cubed x. And now to finish, we just combine some like terms. 2 sine x plus sine x is 3 sine x. And then from here, we have a negative 2 sine cubed. Another negative 2 sine cubed is negative 4 sine cubed x. So kind of a very involved and complex identity, kind of going above and beyond what we did back in section 5.1. You won't see anything like this on Pearson, but we did want to let you see how you can use some of those sum formulas and the double angle formulas all in one single problem. 5.3, much like 5.2, will have assignments that you can work through on Pearson.